Hi, good evening. This is Jayanth Kumar from ID Bombay, and today at ISMB 2024, we will be presenting our poster Enhancing Protein Crystallization Prediction Through Protein Embeddings. This is a joint work done by Jayanth Kumar from IT Bombay, Kavya Jay Kumar from TIFR, and Jayaprakash Sundar Raj from IT Bombay. So let's get started. Predicting protein crystallization is a very pivotal task in structural biology. The reason being that it helps us to determine the protein three-dimensional structure, which is essential for understanding its functions and interactions. Overall, traditionally, this process of protein crystallization has been done heavily through X-ray crystallography, a method which has a high chances of failure rates and it involves a significant cost. Given these challenges, there is a pressing need for more effective predictive methods before going for a wet lab X-ray crystallography approach for protein crystallization, and that's where our research on ESM crystal comes into the play, leveraging deep learning to predict protein crystallization outcomes more effectively. This research presents develops and presents two advanced models: ESM crystal T6-8M-V1 and ESM crystal T12-35M-V2, which are developed based on Meta's ESM42 architecture. Our findings and results show that these protein embeddings actually improve the accuracy of crystallization predictions. The impressive results from both underscore the potential of protein embeddings as a robust tool in predicting protein crystallization, paving the path for a more efficient structural biology research. Okay, so our methodology utilizes a diverse set of data sets, including deep crystal and B crystal data sets, which has both crystallizable and non-crystallizable protein sequences. This approach only touches the protein crystallization problem as a binary classification problem where you have two labels, crystallizable and non-crystallizable. We have used these data sets from B crystal and deep crystal papers. From the deep crystal, we have divided it into training and test data sets. As you can see, the data set is highly imbalanced with only 4,420 crystallizable sequence out of 26,281 total sequences. Similarly, the test data set, we created kind of a balanced test data sets as well as deep crystal test data sets. There we kept a similar number of crystallizable and non-crystallizable test sequences, and similarly we have two other independent data sets, SP dataset from SwissProt database and TR dataset from Tremble dataset. The reason we took a lot of diverse dataset because we wanted to ensure that we can check the robustness of our models. Most importantly, we adopted a transfer learning strategy on top of Meta ESM42, where we leverage the protein embeddings which were already developed from the ESM42 architecture, which enhance the predictive performance by fine-tuning on the specific deep crystal training data sets. As you can see, we only use the protein sequence as an input for both training and inference, and on top of it we take the training data set, we fix the layer of the base model, and then we add on top of it output layers which predicts whether it's a crystallizable sequence or a non-crystallizable sequence as a binary classification problem. Coming to both the models. So the smaller model is fine-tuned on the smaller ESM2 T6-8M model, which has 6 hidden layers, where T6 stands for 6 hidden transformer layers, 8 million parameters, and the model size is approximately 31.4 MB. It is likely faster to train and requires less computational resources, but may capture less complex patterns compared to larger models. The larger and the more complex model, which uses 12 transformer hidden layers and 35 million parameters, has a total size of around 136 MB, and since it has more hidden layers, it can capture more complex patterns in the protein sequence. Overall, as per the results, we get an accuracy of around 78.12% for the smaller model, and we get an accuracy of 80.53 for the larger model on the balanced data set. We employed a variety of metrics including precision, recall, F1 score, ROC, AOC to ensure the comprehensive assessment of their performance. The result was promising, especially if you look at the second larger model. I mean, both models demonstrated higher accuracy, but the ESM Crystal T12 35mm V2 performed better, indicating the potential of advanced protein embeddings in predicting protein crystallization. We also plotted ROC and PR curves. The ROC curves actually depict the sensitivity and specificity, and the PR curve actually illustrates the performance across different thresholds and their effectiveness in handling imbalanced datasets, given that we have a large number of non-crystallizable sequence in the dataset for the training. If you see the area under the curve is around 0.94 and 95 for these models, and this actually shows that the model is robust to different datasets. Okay. Now let's go for the comparative analysis. So as per the comparative analysis, we compared it with multiple papers, which both traditional and non-traditional approaches. So we found that it was superior to traditional and other machine learning based predictors, specifically by just using protein sequences. So if you look at it, generally on for most of the performance wise, the accuracy is around 0.80 for the larger model. If you see, B crystal has higher accuracy, but it uses not just the protein sequences but other information in its prediction. But overall, this shows that the larger model performs really well compared to other models on SP dataset as well and the TR dataset as well. Now let's quickly go into the demo where we can have a quick look at the model. I would just present you the larger model. So this is where you can on this website you can quickly check our model, and you can just input a protein sequence. You don't require anything else, and you can just click on compute and it would go ahead, load the model. And the link of basically the link of these examples, the link of the data sets and all are already there on this website. And specifically if you want to look for, so as you can see, this model predicted that it has 100% chance of getting crystallized. It might be because it has already been crystallized before. Thank you. Thanks for your time.